Hey folks, how y'all doing? Um, we are starting chapter 4 in the book. If you're following along with the book, um, this is an introduction to hash functions. We're going to keep the introduction pretty light today, um, and get into some more of the details next time. So, um, the purpose of a cryptographic hash function is to um, this isn't to keep the message secret. This is to keep the message intact. So this is used for a different kind of thing. It's um, a signature that goes onto a piece of data that assures us that this data has not been altered. So, for example, when we are transmitting a an electronic check from one bank to another, we want to make sure that the amount on the check has not been altered somewhere along the way by a hacker. And so we attach a hash function to the check. And then we make sure that the hash still matches with the data that's on the check. So if we have altered the data, the fingerprint won't be valid anymore. So this is different from the type of encryption we've been doing before, where we don't want somebody to read the message itself. What we're doing right now is just trying to prevent somebody from altering the message by putting this signature on it. So a hash function will take a message of some length and return a binary string of a fixed length called a digest. Now, how is this different from just error correction? Error correction is um, doesn't assume any kind of um, you know, misdoings. It doesn't occur. Doesn't suggest that anybody's doing anything bad. It's just as trying to assume that the connection might be just a bad connection, and random errors may be propagating. Um, and so that we can detect, and correct a certain number of random errors. It doesn't allow for the possibility that somebody is deliberately manipulating the data. Um, because if somebody is deliberately manipulating the data, they can also then manipulate the check bits as well, um, and sneak a message by the error correction scheme. So what we're looking to do is having something that's more robust than just error correction. We're looking to have something that a third party that is intercepting data cannot use to alter the message. So these are the properties that we want a hash function to have. First of all, it should be computed quickly. We have institutions that run, millions of transactions per day. We can't slow down the computation, of these hash digests. So we would like for this to be something that we can do quickly. We want it to be difficult to find. If we have a hash digest, if we have the output, we should be able to have trouble finding a message that creates that output. This is saying it's pre-image resistant. So if I know what the signature is, I should not be able to fake a message that has that signature. I should not be able to artificially create a dummy message that is attached to the signature and have it check out. So I cannot work backwards from the key, or not from the key, but from the digest and construct a message that works with that digest. That should be hard. So this should be an operation that is very difficult to undo. And the other thing that we want to undo is, even if we don't know what Y is, but we know an enemy's message M1, even if we don't know what Y is, we don't want to come up with a second message that we could substitute for M1 because they have the same value for the hash. So we do not want to be able to construct a message that collides, that creates a collision with this. This is what it means to be strongly collision free. There is something called weakly collision free as well. But we want these things to be strongly collision free. So these are the properties that we want. We want it to be fast to compute. We want it to be, if we know the output but not the message, we do not want to be able to compute a message that matches with that output. And if we know a message but not the output, we don't want to be able to construct a second message that would generate the same output, even though we haven't even seen the output. All right. Well, when we say that these things are difficult, that they're computationally infeasible, this is because the size of the digest is going to be small compared to the size of the message. We've got this long data file and this tiny cryptographic signature that goes with it. When I say tiny, I say relatively tiny. And so the function h that creates the hash is not going to be one-to-one. And so there will be examples of colliding messages. The third requirement just says that we should these examples should be so hard to find that we don't have to worry in terms of hackers being able to do this. This is what happens. So if Bob produces a message and its hash, Alice wants to be sure that Bob does not know another message, M prime, that has the same hash. Because then Bob could then substitute M prime for M and then not be detected. That's the idea. Okay? That third requirement has always been the most difficult of the requirements to satisfy. Because if you know what the hash algorithm is like, then you, in theory, could then come up with some way of manipulating your input to that algorithm without changing the output. We'll see an example of that in a moment. So here's the formal definition of what a hash family is. We have a set of possible input messages. We have a set of possible message digests. We have some set of keys as key space for this. And then we have a hash function that takes an input and creates an output from it based on whatever key has been selected. Okay? So we're going to look at an example. It's going to take messages of arbitrary length and creates message digests that are 160 bits long. And the key is also 160 bits long. So the size of our digest is small. It's only 10 bytes. 20 bytes, 8 bits in a byte. So we're going to take a long file. We're going to create a short digest with it. We're going to take the message. We're going to divide the message up into blocks of 160 bits. If there are any bits that are left over, we're going to pad the message with enough zeros to complete a block. And create a digest by XORing all of those blocks along with the key. So if you don't know what the key is, you're not going to be able to recreate this digest. And since there are 160 bits, there are 2 to the 160 possible keys, and this is an enormous number. And so guessing the correct key is not going to be computationally feasible. We're going to XOR all of these blocks together, and then also XOR it with a key, and that's going to create our digest. All right. So let's think about the requirements that we want to have. Is this fast? It's relatively fast. That is, XOR is a fast operation. The size of these blocks is fairly small. N might be very large. If the file size is large, then N is going to be large, but that's going to be the case no matter what kind of hash algorithm we've got. If we're having to process a large amount of data to generate the hash, then that's going to be an issue. But the operation is pretty fast. So I'm going to say yes, this is fast. Is it pre-image resistant? In other words, if somebody gave us a value for y, the hash, could we construct a message that had that pre-image? And unfortunately, the answer is yes. We could just take that hash and XOR it with K and let that be the message. Because then the hash of that message would be, this is only one block. And so it would just be that message XOR with the key, but that's the key XOR with Y XOR with the key, and XORing with the key twice just gives us our Y back. And so this algorithm is not pre-image resistant. And it's also not collision resistant. If I took the original message and I appended some malware that fits in 160 bits, for example. So I'll use B for bad, and I append that twice to the message. Then when we XOR those 160-bit blocks, these will cancel and I'll get the same thing. So any message with a bad block appended to it twice have the same hash. That shouldn't be XOR. That's just, here I'm just concatenating. So not XORing here. Just append a bad block to the, I say the end of the message, but let's be safer and append it to the beginning of the message so that we don't have to worry about maybe the message not having an exact multiple of 160 bits, and we don't have to worry about that zero padding. Okay? So we do some bad block at the beginning of the message, some second bad, the same block again, so that it won't affect the hash, and then the message following that. And then we can prepend any kind of malware we want to onto the message, and it will pass the authenticity check because it will have the same hash. And so this is also not collision resistant. And so this meets the definition of a hash family, but it's not a very good one. This example is not collision resistant. It's easy to come up with a different message that has the same digest. We just talked about how to do that. And so what we want to do is come up with a more sophisticated algorithm than this that will get us a more secure hash. We're going to look at one and talk about the steps in this algorithm. It's pretty clever, and we'll have an example that we can work with on Friday. All right. Thanks for watching.